We welcome you at the Technical Forum at the Group Exhibit Hydrogen and Fuel Cells 2013. Please have a seat and a free drink. Come here and enjoy here with us the next presentation about CFY-Stack as platform for stationary SOFC, SOEC application from the Fraunhofer-Institut for Ceramic Technologies and Systems, Head of Department, Materials and Components, Dr. Kusnezoff. Here we go.
Thank you very much for a kind introduction. And I want to start with my presentation about CFY-Stack as a platform for SOFC and SOEC applications. I give you at first a short introduction about our institute, and then we go deep into details of CFY-Stack, how it is composed and what materials we are using, and then I will give you an overview of the properties of the stack. At first, some words about Fraunhofer IKTS. It is an institute which is situated in Dresden. And in this institute, we have two branches, one in Dresden and one in Hermsdorf. And head office is Dresden, and we have more than 400 workers, and workers are working on different fields in the ceramics, for technical and functional ceramics. And one of the core fields where we are active is solid oxide fuel cell. In the field of solid oxide fuel cell, we have started in 1992 with the development of materials, at first with the company ABB and then with Siemens. And it is also the time where we came to the planar SOFC technology. At first, we have developed sealing materials and contacting materials. After that, we have investigated the electrode properties, and then approximately 1999, we came into the topic of stack development. And now we are covering the whole field of SOFC development, starting from materials up to the systems, and are working together with different partners in this field. Now we are going towards to the commercialization of different aspects of SOFC, and especially the stack technology. If we think about SOFC, then the main application for this technology should be the stationary energy conversion. And it means that we need plants for combined heat and power production. And the idea is that you make such plant from building blocks consisting on singular stacks. And for us, it is important that the singular stacks behave in the right manner. So with low degradation and stable for thermal and system cycling. The idea is that we take such building block and use that for first application, maybe as micro CHP or small energy server, and then we go to the next step, building of 4 such blocks, the next class of SOFC device, which can produce about 5 kilowatt. And then if we combine 8 such blocks, we can produce a device which can deliver us about 6 kilowatt to 8 kilowatt, depending on the number of cells in the stack. And then if you have such blocks which are operating reliably, you can go up to higher power and produce combined heat and power units with the power of 20 kilowatts and maybe up to 100 kilowatts. The advantage of this technology is that we have a very high efficiency, and I will demonstrate it in my presentation on basis on small units, and then you can see that for future applications, also for large units, it will be a big advantage over the existing systems. If we are speaking about CFY-Stack technology, then the name of CFY is the acronym of the composition of interconnect materials, which was introduced by Planse in collaboration with Siemens in year 94 to 96. And these stacks consist of only 4 or 3 parts. If we look through the components of the stack, then you see that the main part or the heart of the stack is a cell based on electrolyte supported membrane, which is covered with 2 electrodes. The other important part is interconnect. Interconnect material is chromium iron alloy, and this part is produced by powder metallurgy. And these 2 parts are sealed with a glass. And the glass has a thermal expansion coefficient which is close to the electrolyte material. And what is important for this is that thermal expansion coefficient of all components is very close to each other. It means the thermal cycling of this stack is not a problem. Only some transients in thermal behavior of the stack can cause mechanical stresses and some damage of stack. But I will show you later how we can handle it and what thermal cycling or system cycling can stack survive. This technology is also utilized in the United States by Bloom Energy, which is very similar to what we are doing, and this technology has also the same roots. But the advantage of this stack is that it has a larger electrode area, and we can produce it also with European suppliers, pure European suppliers. If we look on the stack performance data of the current design, then we see that only 30 cells of this stack can deliver a power of approximately 820 watt. So if we go to the next step and introduce 40 cell, then we come over 1 kilowatt, what is a very good power range for micro CHP applications. The stack is very small, has a good power density, volumetric power density. Of course, in terms of mass or weight power density, it is not so good. So we don't think that this stack is very good for auxiliary power unit or mobile applications. But in terms of volume, it is a very compact unit which can be easily integrated in households. One of the main parts of our investigation is a reduction of the cost of the stack. And the component which defines the cost is interconnect, because it is a repetitive unit in the stack and is produced of alloy which has a very high chromium content. And this issue is addressed by our partner company Planse, and they have experience how to produce such interconnects in millions of parts, because they are supplier of Bloom Energy currently, and now they are struggling on the reduction of the costs, not only on material side but also on the side of manufacturing of interconnect. And you can see that the price of interconnect depends strongly on the number of pieces you produce. And it is a main vehicle how to get to the lower prices, and it is also main or major way how we want to go to reduce the price of the stack. So if we look on the performance of the stack, then you see that we can go up to fuel utilization of 87%. And even at that fuel utilization, we get power more than 820 watt. And we are now in the stage where the cell voltage between different cells in the stack is very close to each other. It means that we have a very reliable production and very repetitive processes in the manufacturing. The testing of the stack occurs always in the hot box. It is not simple furnace testing more. So it is tested like a unit in the micro CHP. So it means that the stack testing takes place in environment which is normally also applied in your systems. One of the big issues of SOFC technology is a long-term degradation. And long-term degradation is discussed in various symposia and in many workshops, and it is known that for stationary applications you should achieve the degradation rate below 0.3% per 1,000 hours. At this time, we are running our stack for more than 8,000 hours with measured degradation of power degradation below 0.7%. And we know also the reasons for these values. And the main reason for degradation is oxidation of the interconnect or interaction between interconnect and protective coating. And we think that with next generation of protective coatings, we can go below 0.5% per 1,000 hours. But you know that real testing for 8,000 hours is also a time issue. So we think that next year we can show you better values, but also the value 0.7% at 820 to 830 degrees C is a very, very good result. Especially for micro CHP applications, not only the long-term stability, but also the system cycling is an issue. In this case, you cannot protect the system with different subsystems from rapid starting or cooling down, and to protect the anode from the oxidation. In this case, you have cycles which we are calling system cycles, which combine thermal cycling and redox cycling. And these cycles we are testing also in hot box, because for this behavior also the thermal mass of the stack and hot box is relevant. Now at this time we have achieved the redox stability or system cycle stability where we see the degradation below 4% for 40 cycles. These tests we have performed in joint program with company Weiland, and at this time we have achieved the current goals for micro CHP. But we think that in the future these goals can be reduced, but of course we can also met these goals by further developing of our product. Now I want to give you some examples of application of these stacks in the system. And I want to start with biogas fueled system, which we have developed at IKTS. Of course, the future biogas fueled systems should be in the range of 50 to 100 kilowatt, but we should start now with smaller systems to reduce the cost of development and to see the problems which we can have by changing the fuel from natural gas to biogas. And here you see the prototype of the system with one SOFC stack, also consisted of 30 cells. And for this system, we have tested operation by CPOX reforming of biogas. This reforming type for biogas has also high efficiency because you have CO2 in the fuel. And if we see on the efficiencies, which we have got in different points of the operation, that you can see that for typical composition of biogas, 40% of CO2 and 60% of methane, we achieve also in this simple system DC efficiency of 47% by a very simple reforming process. We can increase this efficiency if we use anode off-gas recirculation, but now it is still not applied in the system. But it is very encouraging result, showing that also very simple, small systems can operate at efficiencies which are not achievable by any another technology. We have addressed the issue of anode off-gas recycling and a little bit bigger system, which we are developing with our partners in the frame of SOFC 20 project. In this project, we came to idea to make a stack module consisting of 8 stacks. Here in the picture, you see schematical figure of the hot box and the facility or hot box or hot module we have built up with the 8 stacks in reality, and also hot box integrated into full system assembly by AVL. Now I want to show the first results of our tests. It is not the first generation of stack module, it is a 4th generation of stack module, so it is not so easy to integrate also very good running single stacks in the bigger modules. And here you see the operation of 8 units. We have 2 stores, I would say, the floor and the first floor, and we have in every floor 4 stacks. And we can also see that some of them of cell packages in the stacks are not operating so well as another one. We can correlate it also with initial performance of every stack we have measured before. But nevertheless, we can get a very good power output in partial load. So in our testing facility, we have not gone to the full load. Full load would be 5.5 kilowatt. We gone up to self-sustaining operation, or first point of self-sustaining operation. And there we have got approximately 3.5 kilowatt. And here I want only present the comparison of performance of this stack module by the operation in our facility and AVL, and the tests at AVL are continuing now. So you can see the performance of the same stack module now at AVL facility, and we get similar results comparing to that we have seen in Dresden. What we have seen that we have higher temperatures of stack module operation in the system. And this chart gives you an overview of DC efficiency we have achieved in partial load. And this facility has been operated already with anode off-gas recycling blower for now, I think, at all 120 hours with 5 to 6 thermal cycles. If we compare performance of the stack module at IKTS and AVL, we have seen very similar data, but we can also say that the stack module at AVL facility has been operated at higher temperatures. We are now looking for reasons for different temperatures and different performance we have observed at IKTS and AVL, and especially on the thermocouples position we have in AVL facility and at IKTS facility. But what is good, the stack module is operating reliably, and now the system is under first test with all components and is working very well. And now I want to tell only some words about solid oxide electrolysis operation of this stack. So in principle, we have done nothing else. We have exchanged the cells in the stack from SOFC cells to SOEC cells and tried to operate this stack in two modes. In SOFC mode, and then we have switched it and operated it in SOEC mode and vice versa. And we have done it for 40 cycles. And we have seen that the stack with modified cells can operate in both modes. It means that if we can find appropriate cell technology for long-term stable operation for SOEC, then we can use it also as a platform for SOEC systems. And it is a very interesting option to bring the number of produced units in terms of interconnects and in terms of number of stacks. Now I want to give also some outlook for our technology. We are not stopping our development, and we don't say that the design we have developed is already finished. We are continuing on development of MK 350 design, but we don't want to make a big steps in the future. Now we are working more and more on optimizing of interconnect production, on optimizing of manufacturing of the stack, of the yield of all components, of the yield of stack manufacturing, and of course we are going to the to integration of more stack or more cells in one stack to increase the output power. Now we are working with 30 cell stacks, and next year we will start also some commercial or pre-commercial manufacturing of 40 cell stacks to overcome the barrier of 1.1 kilowatt. And one of the big points in our development is the reduction of degradation rate, long-term stability, because we don't see cycling as a problem for our technology. And if we look into stack modules, then we are planning to start first stack modules production this year with 30 cell stacks. And in the future, we want to integrate 40 cell stack in the module. And of course, the stack module is more complicated issue in comparison to micro CHP. And we are looking for partners for testing of these modules in their system to look together for some challenges and also to solve these challenges together with our partners. And I want to acknowledge our current partners we are working with and finish my presentation and give the word back to you.
Thanks a lot for this very interesting presentation. Now you have the opportunity to ask some questions or make some comments or remarks. Are here anything? Sir.
Hello, my name is Theo Holton from Green Hydrogen Consulting, and I would like to ask, you have demonstrated reversibility, if I understand correctly. Do you see any problems in increasing the scale of that to ultimately, well, megawatt scale and, well, ultimately beyond?
Yeah, increasing of the scale is always a problem. It is not only engineering problem, but it is also a statistical problem, because you have a lot of units which are working in one big facility, and every unit should work properly. So I think that this problem can be solved only by very reliable production of the stacks. And we also should look into the range what you need for your application. So I think that the next step for SOFC can be in the range 50 to 100 kilowatt, or maybe up to 200 kilowatt. This step have been made already in United States by Bloom Energy, and I think rather successfully. For 1 megawatt class, it's also, I think, a big step in the development.
It's the question we asked. Yeah. Is there another question?
Can I ask 2 questions? Yeah. The first question I have, you mentioned the pre-reforming. Have you done pre-reforming yet?
Yes, in the SOFC 20 system, we have pre-reformer.
Yeah.
And in this pre-reformer, we realize some definite methane output from reformer, and this reformer utilizes also heat of the system,
Yeah.
and is kept at constant temperature.
So how much is the pre-reforming? How much internal rest is internal reforming, right? How much internal reforming?
Yeah, we have approximately 10 to 12% of methane in the fuel which is going into the stack, at the stack inlet or stack module inlet.
Then rest is the hydrogen, or?
No. It is pre-reformed natural gas, so the rest is hydrogen, CO, CO2, and water.
Oh, I see. Another question I have is, you said the redox. What's the condition? How did you run redox conditions? You have 40 times redox.
Yes. Normally we wait for 2 hours at definite temperature with no flush with oxygen or air in anode compartment. So simply wait for 2 hours. And this is a time which is enough to cool down the facility, or micro CHP facility. Not a large facility, yeah?
And the last question here.
Can you give us about the cost-benefit example? So how much is it? So by example, 50 kilowatt hydrogen fuel cell solution. The life cycle, how long and how much? Do you have any?
What do you mean by benefit? So in principle, your benefit is a cost of kilowatt hour. Yeah, and you should compare it to the cost of kilowatt hour you can produce by competitive technologies. And we have done such calculations, and at this time we are not competitive, but in a large scale we are competitive. Yeah.
For large scale, by example, so 200.
It depends on the application. So if we are speaking about micro CHP, I think that starting with 10,000 units annually, we can become competitive, but with additional funding. And if we go to 100,000 units per year, then we can achieve also breakthrough line. So not very large numbers. It's very moderate.
Okay, thank you for being here again. And if there are any questions left or you like to discuss more, you can follow Mr. Kusnezoff to his booth number B50 here at the group exhibit Hydrogen and Fuel Cells. Thank you very much.
Thank you for coming here and for attention.
And we will continue in a few minutes at 10:30 here with the topic fuel cells for materials handling vehicles from ITM Power. Please be here sitting down and wait for 1 second.